Bismillahirrahmanirrahim. Dear students, let's talk about the second problem of week number 5. This problem is related to a cantilever beam subjected to a VDL. The intensity of VDL is 10 kilonewton per meter. Span of the beam is 10 meter. This point where we have support is point A and the free end is point B. First step in solving any beam is to determine the reactions of the beams. In this case we have just a fixed support, so there will be two reactions, one vertical reaction and a resisting movement. There will be no horizontal reaction as there is no horizontally applied load. So let's see how can we calculate the moment. For moment calculation we will apply the conditions of equilibrium. For reaction calculation, we will apply the conditions of equilibrium. RA is the vertical reaction and MA is the resistive moment. So let's apply sigma Fy equal to 0 first, and our convention is that we will take upward force as positive. So the first upward force is RA, that's acting in upward direction, so we'll take it as positive here, and then magnitude of the resultant of this VDL. We know that the magnitude of the resultant can be calculated as the area of this triangle. Vertical dimension of the triangle is 10, horizontal dimension is also equal to 10. So 10 into 10 divided by 2 is the area of this triangle, and that is equal to the resultant, and that's 50. If we rearrange this equation, we have only one unknown in this equation, and we can calculate that. So RA is equal to 50 kilonewton. The second reaction can be calculated by applying the second condition of equilibrium. Let's take the sum of moment about point A equal to 0, and our convention will be we'll take clockwise moment as positive. RA is already determined, but we are taking sum of moment about point A. So as RA is passing through point A, it will not produce any moment about point A. So only this the resultant of this triangular load will produce moment about point A. The resultant will act somewhere over here. We know that resultant of a distributed load always passes through the centroid of the area. We have a triangular load here, so the resultant will pass through the centroid of this triangle. And we know that from the perpendicular of the triangle, the resultant is base divided by 3 distance away. So base is 10 meters, resultant of the triangular load will pass through a point that is 10 by 3 meters away from support A. 10 into 10 divided by 2 is the magnitude of the resultant, and this 10 by 3 is the lever arm, the perpendicular distance between the load and the movement center. And the tendency of this load is to produce movement in clockwise direction, so it will be positive. And then what else? Then we have MA. MA is in counterclockwise direction. This is our assumption, so it will be taken as negative, and that's equal to 0. If we rearrange this equation, we get MA equal to 166.67 kilonewton meter. Both the reactions of this problem are positive, which means that our assumed directions are correct. Next is to see that what are the portions in which we have to divide the beam. So if we start from point A and we start moving in the rightward direction, there is no abrupt change or any support starting from point A up to point B. At point B the beam terminates, so it means that we will be considering only one portion, and that is portion AB. So we have determined the reactions, and we have seen that what portions are there. There is only one portion, so now we will consider this portion and write down the equation for shear force and bending moment. Although if you remember, we have already solved a problem of a beam subjected to a VDL, but this time we considered that VDL again, and while writing down the equation for shear and bending moment, you will realize that why I have considered the VDL again. Apparently it seems like a simple problem. We have a cantilever beam and there is only one load, but actually the situation is not that straightforward. and that you can see from this diagram. This is the free body diagram for portion AB. The x will vary from 0 to 10 meters, and we have drawn the left part of the beam. The reactions are marked 50 kilonewton in the upward direction and 166.67 kilonewton meter in the counterclockwise direction. These are the reactions that we have already determined. The distance of the section from point A is equal to x, and that's variable. I haven't marked A here, but this point is point A. And the exposed forces are shear force V acting in the downward direction and moment M acting in counterclockwise direction. Now, in order to apply the conditions of equilibrium and get the equation of shear and bending moment, we need to calculate this area, and this time this area is in the form of a trapezoid. So what we will do, we will convert this trapezoid into a rectangle and a triangle. As you can see here, I have drawn a dashed line that is converting this trapezoid into a rectangle, which is at the bottom, and a triangle at the top. And we need to calculate these areas, area of this rectangle and area of this triangle. But the challenge here is that these the dimensions of these rectangles and triangle will keep on changing as we change the location of the section. So we need to sort of derive a relationship between these vertical dimensions, the vertical dimension of on this side and the vertical dimension on this side, in terms of x. For that, we will have to consider the concept of similar triangle. So this is the situation that we have A, B, C. This is the entire triangular load A, B, C, and then this is the location of the section. From point A, the distance up to section is x, and the total distance from A to B is 10 meter. We already know that. So if A to B is 10 meter and A to W is x, then this distance from W to B is 10 minus x. Now let's see, can we calculate this y1? This total dimension is 10, we know that. So comparing the similar triangles, we have two similar triangles. We have two similar triangles. Triangle ABC and triangle WB and V, and we will take the ratios of their perpendicular and base. So this 10 over 10 is the perpendicular over base of the larger triangle ABC, and this VW over 10 minus x is the perpendicular to base ratio of the smaller triangle. VW is the perpendicular of the smaller triangle, and WB or 10 minus x is the base of the smaller triangle. If we rearrange this equation, we get VW equal to 10 minus x, and we know that this VW as labeled here is equal to y1. So y1 is equal to 10 minus x. So now we have got this dimension in terms of x, that's equal to 10 minus x, and we know that this dimension, or as it is shown here, AC total is equal to 10. So if this y1, which is the vertical dimension of the rectangle, that's equal to 10 minus x, then we can also calculate this one. If we call this as y2, so y2 is equal to 10 minus, because 10 is this total dimension, 10 minus 10 minus x, which is this vertical dimension. So ultimately we get y2 is equal to x. So now we have established the dimensions of this rectangle and triangle in terms of x. So let's see how can we write down the equation of shear. Sigma Fy equal to 0 with the convention upward as positive. Now this 50 kilonewton force is acting in the upward direction, so plus 50 minus this rectangular part. Rectangular part is how much? I have shown the resultant of rectangle with red and the resultant of the triangular part in green color. The resultant of rectangle will act at the centroid of the rectangle, so it will be x by 2 from both the sides, from this point and from this point, and the resultant of the triangle will be at x by 3 from this perpendicular of the triangle, and it will be 2x by 3 from this point, which is this location of the section. So if you want to write down the equation of shear, 50 is acting in upward direction, then minus 10 minus x into x. This is the resultant of this triangular load, so rectangular load. So this is R1 basically, and then we have this triangular load which is also acting in downward direction, so it will be negative. And what are the dimensions of this triangle? X is the base and x is the perpendicular, so x into x divided by 2, and then this minus V, shear force acting in downward direction, and that's equal to 0. If we rearrange this, we get V equal to 50 minus 10x plus 0.5 x square. Now in this equation we have x involved, so we will calculate the value of shear for point A as well as point B. At point A, value of x is 0, and at point B, value of x is 10 meter. So we will plug in these values and we will get shear at A equal to 50 kilonewton meter. Sorry, this is a mistake. This is not kilonewton meter, this is kilonewton. And shear at point at B is equal to 0. And is this logical? Yes, this is logical. Shear is always equal to 0 at free end if there is no point load acting at the free end. So if you look at this problem, there is no point load acting at free end, so shear force should be equal to 0 at this point. Okay, so we have determined shear for points A and B. Now let's write down the equation of bending moment. 50 into x. Okay, we have the figure on the other slide, so I'll keep on moving back and forth. 50 into x. Now 50 is the magnitude of the force, x is the lever arm with respect to the section, and it is producing clockwise movement, so it should be positive 50 into x here. Then we have this reaction 166.67, and it is in counterclockwise direction, so minus 166.67 kilonewton meter. And then we will consider this rectangular load first. Now how much is the magnitude of the rectangle? 10 minus x is this vertical dimension and x is the horizontal dimension. So 10 minus x into x is the magnitude of the rectangular part of VDL, and how much is its lever arm with respect to the section? Lever arm is equal to x by 2 because it's a rectangle, and resultant will be acting at the centroid of the rectangle. So x by 2, this x by 2 is the lever arm of the resultant with respect to the section. Now next force is this triangular part, and this triangular part will also produce movement in counterclockwise direction about the section, so it should be taken as negative. And what are the dimensions of the triangle? X is the perpendicular, x is the base, so it should be x into x divided by 2. This x into x divided by 2 is the magnitude of the resultant because it is a triangle. And then what is the location of the resultant with respect to the section? It is 2x divided by 3 because this resultant will pass through the centroid of the triangle. So into 2x by 3, and this minus m is this moment, it is in counterclockwise direction, so we'll take minus m, and that is equal to 0. So this way we have completed the equation of bending moment for the section. If we solve this equation, we rearrange it and simplify it, we get this equation of moment. M is equal to 50x minus 166.67 minus 5x square plus 0.167 x cube. So in this equation again x is involved, so we will calculate the value of moment for point A as well as point B. For point A we will put x equal to 0, and for point B we will put x equal to 10 meters. So we have plugged in these values in the equation of moment, and we have got MA equal to minus 166.67 kilonewton meter. And you can see that at point A we have a fixed support, so moment is not equal to 0. That is very logical. And at point B, moment is approximately equal to 0. Actually, because of rounding off of these numbers, sometimes we get a small value, very small value of moment at free end or at hinge support or roller support. But just ignore this. For example, when you will calculate this this expression, you will get some value in points, 0 point something. We can just ignore that, and MB will be equal to 0, and that's logical because it's free end. So that's this completes our calculation about bending moment. Now next step is to draw the diagrams for shear force and bending moment. Here are the diagrams. First of all, we'll draw the beam AB. We'll mark the reactions 50 kilonewton, 166.67 in counterclockwise direction. Now we have for shear, we have value of shear force at point A, that's equal to 50. Value of shear at point B is equal to 0. So we have value of shear for both the points. Next question is that how these 2 points, this 50 and 0, should be joined. For that, we'll go to the equation of shear, and the equation of shear is a second degree equation. So it means that these 2 points, this 50 here and 0, will be joined through a second degree line. Now the question is whether the second degree line should be like this as it is drawn here, or it should be like this, like convex up. For that, we will look at the variation in the magnitude of the load. The magnitude of the load is decreasing as we move in the rightward direction. So the slope of the curve should also be decreasing. So this is the curve with decreasing slope. If you calculate the draw a tangent here and mark its slope, you will get a larger value of slope as compared to this point. If you draw a tangent here, it's almost equal to 0 here. Now this curve that I have drawn, this freehand curve, it's not very smooth, but that is fine as long as we mark the degree of the curve, that this is second degree, and we can clearly see that this is concave up. So that's fine. Even if it's not very smooth thing, that is okay. Now next thing is to draw the bending moment diagram. For bending moment, we have value of bending moment at point A equal to 166.67, at point B equal to 0. Next question is how should these 2 points be joined? For that, we will look at the degree of the equation. Degree of the equation is 3. So we will draw a third degree line from this point to this point. And I've forgotten to write down the degree here, but but we should always write down the degree here. Okay, so this is a third degree line, and the next question is that should it be drawn convex up or concave up? For that, we will see the magnitude of the shear force. The magnitude of the shear force is decreasing, so the slope of bending moment diagram should also be decreasing. And here is a line with a decreasing slope as we move from A to B. So this completes the bending moment diagram for the beam. Last step is to draw the elastic curve. As the entire bending moment diagram is negative, so the elastic curve should be hogging. And you can notice that near the support, I have kept the slope equal to 0, because due to the fixity, the slope of the elastic curve will be 0 near the support. So the rotation will start as we move at some distance from the support, not right from the support. So here we have the elastic curve. It is entirely hogging. So this completes the solution of this problem. We have drawn shear force diagram, bending moment diagram, and the elastic curve. So I will stop recording here. Thank you very much.